Okay, so we're going to pick up where we left off yesterday, where we were just getting into the cyclo um, alkanes. Now, the bookstore, I'm in contact with the bookstore, and they don't have a copy of the lab packet from last semester because I don't know, they said with the new vendor taking over, they didn't get any materials from 306. So I've got to call them and then or email them out probably to see what we can do. In the meantime, we have um, I've given you dry labs for um, Unit 1 already in a zipped file on Canvas. So you can use that till we figure out what's going on. Worst case is I'll just send you the digital files and we'll just go from there. Okay, so we left off um, with this guy here, and I've changed screens from last time. The same slide, but I've arranged it differently. Okay, so let me do a line drawing version of this. Okay, so there's seven, okay, seven carbons on the backbone. And then we have a methyl on carbon number 2, and methyl on carbon number 3. And carbon number 4, there is a isopropyl group, which looks like that. Okay, so the backbone is 7 carbons long, and we've got 2 methyl groups and an isopropyl group that are not on the backbone but are branches. Okay, so remember when we're naming stuff, it's in 3 parts. The first part is branching. So we have 2 methyls and an isopropyl. The isopropyl alphabetically comes before methyl. So that's going to come first. So it's 4, carbon 4, isopropyl, 2, 3, dimethyl. So whenever you have a di, you have to have 2 numbers here. Now it could be on the same carbon. It could be like 2, 2 or 3, 3. But you got to have 2 numbers that goes with the di here. Okay, and then it's a heptane. So branches, backbone, functional group. Okay, so that's where we left off Monday. So let's get into these cyclic versions. Now, biochemically, a lot of stuff is cyclic. In fact, I would say the majority of molecules are cyclic in the biochemical world. And they're very complex also. That's one of the challenges of biochemistry. Okay, so the line drawing version looks like this here. As we get up to number 6, 6 is the most stable. Of the cyclates. And that's because the bond angles are not strained. So this bond angle is 105.5 degrees. Now, if you remember from 305, we talked about VESPER, and VESPER has to do with the 3-dimensional structure of the molecules. tetrahedral is the most stable, and 105.5 is a three-dimensional bond angle on a tetrahedral structure. Okay. Now, if you notice here on this side,
یا جرمني کې کم کې ترې پښتنه وکړل یو نفر لکونه کې راغله لکونه کې راغله نه ما سره یو ځای پوه شي دا ما دا یو ځای و
you guys turn off your microphone.
خبره ته غوږ شه ما خبره ته غوږ شه شالته د جرمني کې ما سره یو نفر ترې پښتنه وکړل امریکایي خارجي او پوه شي ورډ یور نیم مای نیم از ان د نیم اف الله خان د توبه خدای توبه ګردې مې کلکې نیولې پوه شي قصه یې هر وخت دلته یادوم خلکو ته ما ته یې پوس برا شربون دي درته کوي
You have your mic on.
You guys, mute your mics. Mute your microphones, please.
اسناد مکتب مکتب پرې خوستونو ما زما چې زشرالم اتلس کالو مو
Okay. All right. Are there any questions? Okay, so let's go ahead and go on. So this is the most stable one here, the cyclohexane. The higher up we go, the more strained the angles are. So this one here is the least stable. Being the least stable, that means it's going to want to react faster than the most stable one. So it always goes from unstable to stable. If you're very unstable, it goes to stable quicker than if you are relatively stable to start with. But it always goes in that direction. Okay. Cyclohexane can be in two forms. We talked about this Monday, where we have this methyl and this methyl are close together. Then this methyl and this methyl. Those are the same carbon numbers. Because these are closer, we get steric hindrance. Remember, steric hindrance is where we get. Now, molecules don't like to be close to one another. They'd like to be as far apart as possible. So when we start getting them close together like this, that's putting, that's raising the potential energy of that molecule. Hence, it's not as stable. So this is more stable. This one here. Because of the steric hindrance on the one on the right. Now, biochemically, the steric hindrance is a big deal because this is the way enzymes work. The active site on an enzyme is very, very specific in its shape, in its allowability of anything to come into it. And it's mainly steric hindrance is what keeps that active site so specific. Okay, so whenever you have a cyclic alkane, it's automatically the backbone. So that makes this the backbone. And normally what you do is you choose one of the branches as carbon number 1. Okay, however, you can number it clockwise or counterclockwise. So we can name it clockwise 1, 2, 3, or we could go 1, 2, 3, 4, 5. And this happens to be a cyclopentane because it's 5 carbons, not 6. And then if we did it in black, it would be 4, 5. So if we looked at the black numbering, it would be one ethyl. This is ethyl now. Methyl. One ethyl. E comes before M. One ethyl, three methyl cyclopentane. If we did it in red, the red numbering, it would be one ethyl again. Let's see, one ethyl, four methyl. Cyclopentane. Notice I'm using a dash now to separate the backbone from the branching. They choose not to do that. I think it's clearer with a dash in there. Okay, but remembering to number both clockwise and clockwise on cyclic backbones. Now, we talked about Monday that single bonds can rotate. They can rotate except in a ring situation or a cyclic situation. Then it's rigid. So, not rigid, rigid. If it's rigid, isomers are possible. Okay, so what are those isomers going to look like? We can have 1,2-dimethyl cyclopentane and 1,2-dimethyl cyclopentane. What's different about them? It's the orientation of the two methyl groups. Now, one, it's cyclic. That means that those carbon-carbon bonds are rigid. So we need to designate this one from this one. It has to do with whether they're on the same side or not, or opposed. Now, you've heard of trans because of the trans fat in nutrition. Trans fats are also widely available whenever you modify a fat. You usually end up with trans fats. The natural orientation for fats is cis. So trans is more stable. And it's more stable because, again, of steric hindrance. Okay, methyls are farther apart over here than they are over here. And that makes it more stable. Now, a way to remember this is cis, think of sister. Sisters are close, usually, at least after they get past teenage life. Okay, so again, steric hindrance comes into play. It's going to come into play a lot during this semester. Okay, physical properties of alkanes. They're basically non-polar. Our world, biochemically, is a water world, which is very polar. Hence, we have a solvent system in our body that is mostly made up of water. If it was made up of pentane, we'd have real problems. Now, the thing is, fats are also non-soluble in water. So our body has to make arrangements to make those fat molecules polar. So it converts the triglyceride fat into a fatty acid, which are polar. Anyway, they typically are low density. That means they float. And then as the molecule gets bigger, the boiling point and melting point goes up as well. That's true with whether it's polar or nonpolar. Okay, this is an example of a fatty acid we're going to be talking about in Unit 3. Unit 3 is on acids and esters. Okay, so notice this thing. It has an acid end and a non-acid end. Okay, this is very polar, and this is very nonpolar. But because of the acid end, it can be dissolved in water. Not very easily, but it can be dissolved in water. Now, we're going to be making soap in one of the wet labs, and this is one of the fatty acids we're going to be using. Okay, as the alkane gets bigger, the boiling point goes up. So this is size and mass. Density changes a little bit as well. Still less than 1. Density of water is 1. So anything less than 1 will float on water. This is it in graphic form. Now we're going to be seeing this throughout the semester, looking at different functional groups. I'm going to be putting in different lines depending on what the functional group is and how polar the functional group makes the overall molecule. Okay, now I'm going to hold off talking about reactions till we get into alkenes. There are only 2 reactions for alkanes. One is combustion and one is halogenation. Combustion means it burns to carbon dioxide and water with a spark. Okay, so that's alkanes. Now we're going to get into alkenes, double bonded carbons next. And that's when the reactions multiply quite a bit. I mentioned that on Monday, and we're going to get into it today. Okay, so any questions about alkanes that we went over today?
I got one. You mentioned that when you have a cycloalkane, you choose one of the branches as carbon one. How do you decide which one is carbon one? This was back in the naming slide.
Yeah, let's go there. Well, you look at the branches. This is an ethyl branch, a methyl branch. And you know the ethyl alphabetically is lower than the methyl, E versus M. That's a good place to start carbon number 1 on that one, the first branch
Okay.
in your naming. It really sort of doesn't matter. For example, if we started numbering over here, let's okay, if we started numbering over here, we'd go 1, 2, 3, 4, 5. So it would be 2 ethyl, 1 methyl, cyclopentane. And on a test, if you put this down, I wouldn't mark it wrong because it's very persnickety incorrect compared to this one. Um, but if you were going to choose between which one you're going to be carbon number 1, I would just use the one with the alphabetically the lowest value.
That makes sense. Thank you.
Now, the reason why I'm having you name stuff is so that you look at the structure. because you can't name anything unless you understand the structure. So that's why every test is going to have naming on it. Okay. Um, and remember when we get into cyclic stuff, there's rigidity and you can have isomers, cis-and-trans isomers. Okay, so let's jump over to alkenes now. Unless there are any other questions about alkanes. Now, your first couple pages of the Unit 1 dry lab involves alkanes. And then it gets into alkenes and alcohols. Okay. Okay, I've got to do one thing first here. Okay, we have saturated hydrocarbons and unsaturated hydrocarbons. You've heard of that from fats. We have saturated fats, unsaturated fats. When we start with unsaturated hydrocarbons, we're talking about double bonds and single bonds in the molecule. Triple bonds are triple bonds, double bonds, and single bonds. Now, we're not doing alkynes because they're not native to biochemical systems, at least the common biochemical systems like mammalian physiology. Also, we're not going to cover plastics. We're going to be covering polymers, but we're going to be covering biological polymers like uh, carbohydrates, proteins, and fats. There are polymers in those but they're biological polymers, not plastics. Okay. Now we're going to be covering something called aromatics also. Now aromatics are alternating double single, double single, double single bonds. And these are inherently more stable because of this alternating double single, double single, double single. It has to do with the way the electrons along the double bonds align. And so aromatic compounds tend to be extremely stable. Okay. Now, when we're naming, I want to remind everyone that we're going to ignore the monodiatribe when we start alphabetizing stuff, except for iso, like isopropyl or isobutyl. Okay, so we have a double bond. So the functional group with alkenes is going to be the double bond. So that's going to determine the backbone. Doesn't matter how the backbone looks, it has to contain functional group. No exceptions. Now, with the alkanes, the functional group was a hydrogen, and it sort of was all over the place. So that's why you had to look at the one that was the longest and all that stuff. But with all the other functional groups, there's alcohols, double bonds, aldehydes, ketones, acids, esters, amino groups, amides. There's a whole bunch of them, functional groups we're going to be studying this semester, and those have to be on the backbone. So when we're drawing the backbone here, we have to include that double bond. And the numbering is going to dictate the lowest number that includes the backbone, the functional group on the backbone. So in this case here, we numbered from right to left. If we numbered from left to right, the double bond would be in the higher numbers. So when you name this stuff, you name it where the double bond starts. Here it starts at carbon number 2, the red. The blue starts at carbon number 4. So the 2 is shorter or smaller. So that's why we would name this 2-hexene. Also notice that there's 2 ways to draw this butene up here. It's like this and like this. So this would be cis butene. This would be trans butene. Okay. So if we're looking at this 3-methyl-1-butene, okay, start with the double bond or the backbone. It's going to be here. Got to remember, it's got to contain the functional group. And there's 2 ways we can do that. So let's choose a different color backbone. We can also do that. Okay, the orange or the yellow, both are valid. In the case of the orange, carbon number 4 is going to be the branch. With the yellow, it's going to be carbon number 3 is going to be the branch. Okay, so let's erase that one. Let's go with the yellow one. Okay, so we have a branch here. This is a methyl branch. So it's going to be backbone is 4. So that's going to be a now the functional name for a double bond is an ene instead of an ane. So it's going to be butene. And where is the double bond? That's an N, by the way. Okay, so where's the double bond? The carbon number 1. Now, if we name from right to left, it would be carbon number 3. Okay, and then we have a branch at carbon number 3. So it's going to be 3-methyl. And I need more room. Let's see. 3-methyl-1-butene. Okay, so now we have to have numbers for the functional groups. Sometimes the functional group is always on the end, like aldehydes. And then it's optional to put the number in, but that's the only one. All the rest you have to number them. Okay, so does that make sense where you have to say what carbon the double bond is on? Now, some of you might say, well, why couldn't it be carbon number 2? Because we're going in this direction in the numbering. So when we first hit a double bond, it's at carbon number 1. If you're going the other way, it would be the other carbon, but then it would be a higher number. Okay, so let's look at this one here. We numbered from right to left. And if we numbered from left to right, the beginning of the double bond is going to be a higher number. So let's do that in blue. So using the red numbering, the first double bond starts at carbon number 2. In the blue, it's carbon number 4. So we're going to use the red numbering. Okay, so it's 6 carbon long. That makes it a hexene. Because it's a double bond, we have to say what carbon the double bond starts on, which is carbon number 2. And we have a branch at carbon number 4. So let's get our backbone on. And that's at carbon number 4. That's 4 methyl 2 hexene. Okay, so the only tricky part with hexene or alkenes is what carbon number does a double bond start out? So in this case, since we started on numbering on the right, the first time we hit a double bond is on carbon number 2. That's why it's 2 hexene. You can also have multiple double bonds. Okay, so if we look at this guy here, oops. We've got 2 double bonds here. Got a double bond here, double bond here. Now, in this case, it doesn't matter which way you number because of the symmetry. Okay, if we use the blue numbering, the first double bond appears in carbon number 1 and carbon number 3. If we use the red numbering, it's on carbon 1 and carbon 3. So both of them are equal. And it's also a very symmetric molecule. Now, we're going to be talking about when you have a mixture of product in a reaction, you're going to have to determine which is more stable of the mixture. One of the metrics we're going to use is called symmetry. In this case, this is a very symmetrical molecule. So the symmetry would be very high with this molecule because it's balanced. Does that make sense in terms of what this looks like, symmetrically wise? Let me show you an unsymmetrical molecule. See how it's kind of lopsided, where the red one is not lopsided? So between these two, the one on the left, the red one, is more symmetrical than the one on the right. So if we had a reaction and these two were the products, we would end up circling this one as more stable. There's another metric we're going to be using. It's called Markovnikov's rule. I'm going to get into that a little later. So there's always 2 factors you're going to be using. One of them being symmetry. Okay. Now, because we have two double bonds, we have to indicate the di, meaning two double bonds. Whenever we have a di, we have to have numbers that correspond with the di. That's a carbon number 1, carbon number 2. Same with here. We have a di. Has to correspond with two numbers. And remember, you can have branches on the same carbon. For example, if we had say in this molecule here, we had that. Okay, so we've got 3 methyl groups. Okay, one is on carbon 2, so this would be 2, 5, 5 trimethyl 1, 3 cyclodiene. Cyclopentadiene. So we need 3 numbers. Okay. So on the right-hand molecule, the double bonds can appear in cyclic molecules as well. Double bonds do not rotate. That means they're rigid. No free rotation means rigid. If it's rigid, look for isomers. We mentioned cis-trans earlier. Again, frequently you'll have a cis-trans combination. So since the methyl groups or the hydrogens are on the same side, cis. Here they're opposite sides, so it's going to be trans. And they have slightly different physical properties as well. I said earlier the trans is more stable because of steric hindrance. So that means the more stable one is going to have a lower boiling point. Density, it's hard to judge on what the densities will be, but for sure on boiling point and melting point. The more stable one is going to be lower. And it has to do with steric hindrance again. Okay, physical properties. This is when I say physical properties, I'm talking about intermolecular forces, IMFs. Similar to alkanes, nonpolar and soluble in water, soluble in nonpolar solvents. So when we have these guys in our body, we have to have some way to make them polar. So they are motil. The motility of a molecule in our body has to do with its polarity. For example, you give an injection. If what you inject into the muscle or underneath the skin is polar, it can be picked up by the lymphatic system or the blood system and carried away. If it's nonpolar, it's going to sit there for a long time. Let me give you an example. When I was little, I had really bad asthma. And the only thing they could do for asthmatic back in the 50s is give them vitamin B12 shots. And they were very viscous shots, and they had to give them to it in your butt. I could not walk for 2 hours after they gave me that shot. because it was such a non-polar um, uh, vitamin B12 mixture. It was awful. And it really didn't help me that much either, which is the sad part. But anyway, that's all I had. Remember, my dad used to, when he'd take me, we'd always stop at a 5 and 10 cent store on the way back. He'd buy me these little cheeks. They're like little bitty um, ducks and stuff, and just to take my mind off the fact I could barely walk. Anyway, so motility and polarity are very interrelated, and that has to do with how well something will move in a certain solvent. In the case of biological systems, it's going to be water. Okay. Um, Similar pattern as to the alkanes. The bigger the molecule, higher the boiling point, higher melting point, and density um, changes, but it's non-predictable. Like you can't say always that the density goes up the bigger the molecule. Okay, reactions. Now, this is going to get complicated starting now. Are there any questions up to this point about naming these guys or anything like that? Okay, you'll be practicing that in your dry lab. Okay, there's a number of different types of reactions. Um, let's pull up the flow chart. Oh, I had it right here. Okay. Um, Notice alkanes, there's no real reactions. With alkanes, there's halogenation and combustion. Okay, with alkenes, there are five reactions. There's combustion, turning an alkene into an alcohol, turning it into a halogenated alkane, turning it into a halogenated alkane, only with a different formula though, and then putting hydrogen across the double bond. So there's five reactions for alkenes. Okay, the first one is called an addition reaction. That means we're adding something to the double bond, and we're converting it from a double to a single bond. And then what you're adding to it is added onto each of the two carbons representing the double bond. So, and there's two kinds of add-ons. Let's see, let's put that over here. There's homogenetic and heterogenetic. Okay, this is like, and this is unlike. So notice BR or CL, those are like. So that's going to be a homogeneic addition. H2, that's HH. So that's, again, a homogenetic addition. Water is like this as it adds. Water is a hetero because these are unlike. Same with HCl. So those are hetero again. Now, combustion is not an addition reaction. It's a it is a oxidation reaction. Okay, so when we're adding across a double bond, we have to consider the add-ins as either homo or hetero, because you're going to get a different product each time if they're homo versus hetero. Okay, so this would be homogenetic. So each one of these is going to add across. Okay, so this single bond is 2 electrons, and there's 2 electrons as part of that double bond. In fact, let's do that in different colors. So that's where the 2 electrons for this left-handed bromo comes from. And one of the double bonds comes out and bonds to the bromo as well. So we're not taking electrons away, we're just rearranging them. Okay, so let's give an example reaction here. Let's take that, and this is, now whenever we have a reaction, all reactions the name reactants, name products, and conditions. Okay, so let's take this and we're going to add bromine gas. What do we get? Okay, so we've got, oh, by the way, one other thing. Um, double bonds are unstable. It has to do with where the electrons in the double bond are located, and that's what makes it unstable. And we're going to a single bonded carbon, so that's stable. Okay, so this is a natural process because we're going from unstable to stable. We don't have to add any heat, we don't have to add any catalyst, nothing. Okay, so this is going to be 2-butene. Conditions are those are the conditions. And what does it give us? Okay, the BR, each BR lands across the two carbons in the double bond, so we end up with and that's going to be 2, 3 dibromo butane. So on a test, I could say, I cover up the product and says, what happens? Or how do I make 2,3-dibromo butane? So the 2-butene would be a precursor, one way to make it. Now, when you're adding homogeneic addends, you don't get a mixture because they're the bromines are the same. When we have a heterogeneic, excuse me, situation where we're adding, you get a mixture. So homo, no mixture, hetero, mixture. So these are homo, so no mixture. Now, in the flow chart that I gave you, I will actually notate that. Expect a mixture. Now, when you expect a mixture, 98% of the time you get a mixture. Sometimes you get a mixture, but the products are the same molecule, just flipped over. Okay, so does this make sense where you're adding Br, a bromine gas across double bond? This is probably the simplest reaction when you're working with homogeneic add-ons. Okay, so let's go on. Now let's add hydrogen gas to double bond. So we go from a alkene to an alkane. Homo, no mix. Now this is a very common commercial process. It's also a process biochemically where we take an alkene and actually reduce it to an alkane. Okay. Vegetable oils can be saturated and unsaturated. The unsaturated vegetable oils have a lot of double bonds in them, from 1 to 6 double bonds. Those are called polyunsaturated. If you hydrogenate a polyunsaturated fat, you end up with a saturated fat. So its physical properties change when you hydrogenate it. So that's how they used to make, well, let's do an example here. That's how they used to make vegetable oil act like lard. Back in the 50s, my mother was health conscious on the food she used to prepare for us. And at the time, it was felt that lard for baking, like pie crusts and stuff, was considered very unhealthy. It still is to the point, but it's anyway. So my mother chose Crisco as a substitute for lard. The problem with Crisco at the time, they made Crisco by hydrogenating vegetable oil. Now, remember I said earlier that the trans is more stable than the cis? The problem when they started hydrogenating the oil, it converted the cis double bonds to trans double bonds. in the process, which made the fat very unhealthy. So I grew up on eating very trans fats. I'm living proof that it won't kill you, but makes your hair fall out. If you've noticed the back of my head. Okay, so let's do an example here now. Let's take and let's take a butene again. And this time I'm going to do it with hydrogen gas. But with hydrogen gas, the reaction is slower. So what they do is they throw in a metal catalyst, like platinum, for example. Any metal, any active metal works fine. Platinum is used a lot because it doesn't react. It just acts as a placeholder for the reaction to happen. So it's regenerated. Okay, so let's name this. This is going to be 2-butene again. And the H will look like that, H2. So it's going to add to either side of these carbons here. So you're going to end up with butane. Because this is going to be an H here and an H here. No mixture because it's homogenetic. Okay. Now when there is a heterogeneous addition reaction, expect a mixture. Okay, a guy named Markovnikov, a long time ago, about 150 years ago-ish, came up with a rule trying to determine of the mixture which is going to be more stable. And he said the terminal hydrogens, excuse me, the terminal carbons, so that's a terminal carbon. You count the H's. This has 2 H's. This has 3 H's. If we look at this molecule, H, 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 this has 3 H's here, 3 H's here. So 5 H's versus 6 H's. So the one on the right is going to be more stable than the one on the left. So if you had a mixture and these two were the mixtures, made up the mixture, you would say the one on the right is more stable and you'd circle it. Also, it's more symmetrical. This is lopsided, the one on the left. The one on the right is balanced. So you're going to have an S and an S for symmetry. Symmetry loses. M for Markovnikov, 5 versus 6, it loses as well. So that's why you circle it, because the S and M are more favored than the one on the right versus the one on the left. Okay. So let's start off with our first heterogeneic add-on, HCl. So we're going to, H is going to add to one side, Cl is going to add to the other side. However, 50% of the time, this H is going to add to this one, and this Cl is going to add to this one. So you end up with this. And there's your mixture. So then you have to look at which is more stable by using the Markovnikov rule, and secondly, symmetry. Okay, so let's look at some examples here. Let's look at and so this is going to be 1, 2, 3, 4, 5. So this is going to be 2 pentene. If we count from left to right, it ends up being 3 pentene. So 2 pentene is more correct. Okay, so we're going to add acid, hydrochloric acid, and we're going to get a mixture. And the HCl is going to be on one time, it's going to be here, like that. And the other time is going to be like this. Okay, so which is more stable? So look at symmetry.
The first one.
Which one?
The first one. The 2-fluoro pentan.
Okay, so let's look at symmetry. Which one is more symmetrical? Look at the location of the chlorine.
The first one.
Okay, the first one is on the second carbon, right?
Yes.
And the one on the right, it's on the middle carbon, carbon number
Yeah.
3.
3. Yeah.
Okay, so the one on the right is more symmetrical about the Cl than the one on the left. One on the left is a little lopsided. It's lopsided to the right. The one in the middle, the chlorine is exactly in the middle. So it's symmetrical. I should say it's more symmetrical than the one on the left. What about the Markovnikov rule? Let's look at terminal hydrogens. Okay, we have how many here? 3 hydrogens there. 3 hydrogens here. 3 hydrogens here. 3 hydrogens here. So what about Markovnikov? What would Markovnikov predict the most stable? Left or right? Neither. 6 H's versus 6 H's. So we can't use Markovnikov. We can only use symmetry. That one's more symmetrical than the one on the left. We also have to name these. So this one's going to be 2 pentane. This one's going to be 3 pentane. Okay, whenever there's a mixture, you always have to circle the one. And I'm talking about like 40, 60%, 30, 70, 45, 55. There's always going to be a more stable version. Okay? So we've named the reactants, the products, and the conditions.
So
Yeah.
why didn't you put the chloride, like a 2-chloropentan, or the nomenclature? Yeah.
I didn't follow your questions. Say again.
You didn't put the Cl in the nomenclature.
Yeah, the S, you're talking about SM, right?
Yes.
Yeah. S stands for symmetry, M stands for Markovnikov. So M for Markovnikov. You can also write it out if you want. It's a long, he has a long name. And symmetry is going to be S. Does that answer your question?
Professor,
Okay.
I was thinking that we should put two chloropen pen pentan or three chloropentan.
Oh, I see what you mean. You're right. This should have been, yeah. I'm sorry. Yes, you are very right. Two chloro and three chloro, right?
Yes, sir. Yes.
Thank you.
You're welcome.
Okay. Every day I prove I'm human. Every day. Well, over the summer, I was really sick. I had a cough that was lingering, and I would be making mistakes regularly. Okay. Yes, that's right. Two chloro and three chloropentane. Ah, okay. Hydration. Hydration is the act of adding water. Okay, so, and water is hetero. So let's do an example adding water. So let's start with now when you add water, you have to add it with an acid catalyst. You can say H plus, or it's always sulfuric acid we're adding. I like to put H plus because that's what's active. The sulfuric acid, there's a bunch of spectator ions there. Um, okay, so this is going to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that's going to be 2 pentene. We're going to add water, acidic water. The water is going to add, because it's hetero now, you're going to get a mixture where the OH is going to be here once and the other OH is going to be there. So once it's going to be here, and the other time it's going to be here. Now these are alcohols. We haven't got to the alcohol subunit yet, but the way you name them, alcohols are OL, functional group. So we have 2 pentanol, 3 pentanol. Okay, you all see how I got those? The water, remember the water's like this. We have the H and OH, and then we flip it and for one of them, and then we flip it for the other one. So the OH is in 2 different spots, basically. Okay, so we have SM, SM. Okay, symmetrically, which is more symmetrical, right or left?
Right.
Yes. The left one is skewed to the right. What about Markovnikov? Got 3 H's here, 3 H's here, Three H's, three H's. So Makovnikov doesn't work because the H terminal H's are the same. So the only thing we got to go on is symmetry. And those are the addition reactions. So when we add a homogenetic one, no mixture, we add a hetero, it's usually a mixture. Sometimes it's not a mixture. Okay, as far as the test goes, I will never give you a situation where you're adding a hetero and not getting a mixture. I'm gonna make it very clear. Okay, so those are the reactions of alkenes and combustion. So if we did this, say we took the 2-pentene and with a spark, we would get water, carbon dioxide, which is an oxidative reaction. Okay, those are the reactions. Let's talk about an aromatic compound now. So we can divide compounds up into aromatic and aliphatic. Aromatic contains benzene. That's what this here is. Benzene. Or 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 benzene rings that are tied together, like this here. Those are pretty common in our environment and in our bodies. Okay, so aliphatic does not contain any benzene structures. Aromatic contains at least one benzene structure, and it could contain lots of other aliphatic parts. But if there's one benzene in there, it's called, the whole thing is called aromatic. And we usually draw it like that, not like this. Okay, now another interesting thing is that there's only one bonding site here. If you have cyclohexane, there are two per carbon. That's what they're talking about here. Okay, so to name benzene, there's a lot of different ways we're going to be looking at benzene. In fact, yeah. So the branch will determine the name. So bromobenzene, chlorobenzene, NO2 is a nitrite nitro group. So that's nitrobenzene, and then this is an ethyl branch, so it's an ethylbenzene. However, these are specialized branches. If there's a methyl group, not an ethyl, over here we had an ethyl. If it's a methyl, it's called toluene, not methylbenzene. Toluene. If it's an OH group, an alcohol, it's called phenol. It's got an NH2 on it. That's an amino group. It's called aniline. And if it's got an acidic group on it, it's called benzoic acid. Now, the weird thing about benzene, now up here, the benzene is the base. Up here, the benzene is not the base. This is the backbone. The benzene is a branch. When it's a branch, so this is a branch here. Notice the backbone doesn't go through that benzene ring branch. Okay, so benzene changes name to phenol. Instead of benzene. A lot of students make mistakes and they'll call it benzyl. And it's not benzyl, it's phenol. I will never do this. I will always draw the benzene ring, like this here. I don't like doing the C6H5. Notice again, it's phenol. So it's 1,1, so the phenol group is coming off of the same carbon, so it's going to be 1,1 diphenyl cyclobutane. Okay, so if it's the base, so basically that's the backbone. If it's the backbone, it's a benzene-based name. If it's a branch, it's a phenol name. Now, this is a really old world way of naming regarding branches off of benzene ring. If there are two branches and they are the same, depends on, in this case, it would be 1, 2. This would be 1, 3. This is 1, 4. So we're going 1, 2, 3, and then 1, 2, 3, 4. Okay. If they're together, you go, this is italicized, O dash. So that is the ortho. Think of or, little word, close together. P stands for para. Think of a paraglider. Wings are out each side. Wings are out each side. And then the one in the middle is meta. But this is an old world, and it's naming, and has stayed around. And then we can add on different things and then you end up with a backbone of the benzene again. So it's going to be a benzene name base, not phenol. Okay, aromatic compounds are like alkanes, and alkenes are nonpolar, not soluble in water. They don't like water. Um, Now, the important thing, though, on this is aromatic compounds are very stable because of that um, double single bond alternating. They're very, very stable. So because they have double bonds in it, they can't undergo addition reactions like we did earlier today. Okay, there is one. So these are all aromatic because they contain benzene rings. These are also very carcinogenic, including benzene. Very bad for you. They found out these are carcinogenic because when um, um, in the Midwest they had chimney sweeps, and they noticed the chimney sweeps were getting um, cancer more than the average person was getting. And they narrowed it down to these creosote-like compounds formed on the inside of your chimney, and that is very bad for you. So if you have a chimney and you burn wood in it, creosote will build up in there. Do not clean it yourself. Have a professional clean it because they've got special stuff to absorb the dust. And if you do it yourself, you're not going to have that, and you're going to end up inhaling that. And the worst possible way to get a carcinogen is in your lungs. It's distributed very, very nicely throughout your body, and it's just really bad. I think they got bladder cancer, but anyway, it was definitely a cancer though. All right, so that concludes our unit on alkenes. And we didn't go to 2 o'clock too, because I was ended up being late on Monday. Okay, so the hard part of alkenes are the reactions. And these you need to practice a lot. That's why the Unit 1 dry lab worksheets are really valuable. You're going to be practicing alkenes and alkanes, and then also alcohols. We haven't talked about alcohols yet. Okay, are there any general questions about alkenes besides being harder than alkanes?
Could you do an example where Markovnikov's rule
Yeah,
has more of an effect on
yeah,
the
yeah,
results of an addition reaction?
yeah. Usually it's when the double bond is on the end, because then the hydrogens coming off of the double bond on the very end is only two. So okay, so we've got 1, 2, 3, 4. So this is one butene. And so the HCl is going to add here and here. So we're going to get like that. Okay, so let's look at symmetry. And we're going to look Okay, Markovnikov. Okay, which is more symmetrical, top or bottom?
Bottom.
Bottom. I agree. Okay, what about Markovnikov? Okay, we got three H's here, two H's there, three H's here, three H's there. So Markovnikov, 6 versus 5. So Markovnikov wins on that one too. And this would be one chloro, 1, 2, 3, butane. This would be 2 chlorobutane. So usually when that double bond is at the end here, when it's in the middle, you've just got a regular carbon on the end, and those regular carbons take 3 hydrogens apiece. Is that better?
Yeah, that helps a lot. Thank you.
Good. Now, frequently on a test, I'll ask you two kinds of reaction problems. I'll say, cover up the products. I said, if you got 1 butene in an acidic environment, HCl, what do you get? The other type problem is I'll say, how do you make 2-chlorobutane? What's the precursor for 2-chlorobenzene? I mean, 2-chlorobutane. Let's do an example of that. So I want to make this. How do I make that? Well, you have to look on your flow chart. So let's load a flow chart here. Okay, so how do you make an alcohol? Right here. Well, you can make it from an alkene. And normally you would take the backbone being the same. Now we're going to see in the alcohols, there's one exception to this, but basically the backbone remains the same. So if it's a 5-carbon backbone that you end up with, you're going to start with a 5-carbon backbone. Now, down here is where that doesn't work. That's the only one. All the rest, that holds. Okay, so how do you make a 6-carbon alcohol? Well, you make it with a 6-carbon alkene. Okay, so 1, 2, 3, oops, 2, 3. Okay, and it comes from an alkene, so the alkene can be here because you can get an OH here adding, or an OH here adding, so that gives us our middle OH. We put it over here, that would work as well. We'd have an OH here or an OH there. So that's what we start with. So let's just use this one here. So that's going to be 2-pentene. 1, 2, 3, 4, 5. Carbon number 2 is where the double bond starts. And this is going to be 2-pentanol. Condition is going to be water and an acid. So that's the kind of questions you'll see. In fact, let me show you one other place you can go. If you go to Files and Test Related, you can look at these practice tests. Unit 1 practice tests. And there's a whole bunch of practice tests, 12 of them. Now, this Chem 131, that is the equivalent class up in Tacoma, where I used to teach this class. And some are docs, some are PDFs. So name it, all names. Reactions. So how do you make that? How do you make that? Now, we haven't talked about two-step problems yet, but that's part of the challenge of reaction. Sometimes it's one step, sometimes it's two steps or three steps. Now, you're going to have a take-home problem for most of the tests, all four of them. And that'll I'll give you plenty of time to do it, and it'll probably be a synthesis problem with multi-steps. Anyway, so this is the test I gave last spring. But anyway, up in Washington, I was required to not use line drawings. So I was stuck using these. Anyway, well, this is an interesting problem. My dad was in the Air Force, and we were stationed down at Homestead Air Force Base, which is south of Miami. Tons of mosquitoes, tons. So this is what the Air Force Base would do to the mosquito problem. They told us to put a teaspoon of gasoline on all the puddles in the yard. What that would do, mosquitoes could not lay their eggs on water with gasoline on it because gasoline would float and they couldn't land on it. They would sink. And gasoline floats on water because it's a hydrocarbon and its density is less than 1, so it floats on the water. And it's also extremely bad for the environment, but that's the way the Air Force did things. They still do it that way. Anyway, this is a true problem. Anyway, so you've got some practice problems, practice tests to study from as well. And basically, the day before the test, I usually go over one of these practice tests. It'll probably be this one here. So you've got these guys, you've got dry labs. You go to the worksheets. These are parts of the Unit 1 dry labs. I just combined all these together into a zipped file. And here's some more problems. These are multiple choice. So it's more practice. You can do this digitally, do them, print them out and do it on a worksheet. You can email me questions or you can ask me questions during lecture, either way, or during lab. Lab's probably better because I'll be right there. Um, okay, so what do you think? This is quite a difference between 305. Yeah, so a couple people asked me, this is pretty wild stuff here. And you've never seen it before. There's one person in our class that has a degree in biochemistry. So she's seen this many times, but everyone else, you've never seen this stuff before. So it's going to be really foreign to you. So it's consistent that you're confused. It's just a matter of spending the time. If you don't spend the time, now the problem with this class is every unit builds upon the prior unit. That's why every test, except for test one, is a final. So test two requires you to know unit one stuff. Things like naming, structures, how do you do a reaction. If you don't know how to do that from unit one, unit two, you're going to die. So you've got to spend the time early on. Don't get behind. It's really hard to get caught up in this class. The way I've structured the class, your labs help you a lot, points-wise. They require a fair amount of work, though, but it's not hard work. It's just work. I consider lab points easy points, test points hard points. You want to maximize your easy points to go against your hard points, test points. Additionally, there are some opportunities for extra credit. One is to decorate your lab coat. As you saw mine on the front cover, it's very tie-dyed. I like color. Now, most teachers require you to use black or blue ink on your lab reports. I like color, so you can do them in any kind of color you want. You can decorate the pages. Some students really like to do that, and that's great. Encourage you to do.
Professor, I have a question.
Yeah.
Being that I was in your class for 305 and I already decorated my lab coat, can I get points for that, or would I have to get a new lab coat?
No, you get points for your decorated one.
Cool, thank you.
Yeah, the advantage of having me for 305 is you can decorate your lab coat and carry it with you. So definitely don't buy another one. Now, your project is also another way to get points. Most people, not all people, most people do pretty well on their projects. Most people get, I shouldn't say most, a lot of people get full credit on their projects. And it's something of interest to you. I'm going to talk a lot about that as the semester progresses. And they're due anytime. Say you do it this weekend, or you do it over Labor Day, you have the long weekend, and you get it done. Turn it in. It's due anytime in the semester. Most people wait till the very end. About halfway through, you're going to have a topic. That'll be an easy 11 points, but you have to have a topic by midterm. I forgot where. I haven't put a due date on it yet, but basically, after about 7 or 8 weeks, you should have a topic by then. Okay, anything else? Let's see the chat here. Okay, a couple things here. Flowchart is located. If you go to files, Unit 1. Where are they? It should be under worksheets. Yeah, if you go to Unit 1 files, it'll be at the bottom. I notice I put expect mix. Expect mix when you add water because it's hetero. Expect a mix. This is hetero here. Anyway, that's where to find the flow chart for Unit 1. And then for Unit 2, yeah, Unit 1. What I do with the flow charts, I start with Unit 1 and I keep adding to it. For example, this is here at the bottom is what I added to Unit 1. You can see there's a lot of reactions. Okay, so anyway, that's where to find the flow chart. I would definitely um, print that out and have it with you. It's like a periodic table in 305. Um, use it all the time. Okay, so let me go back to the chats here. You can use any kind of materials you want to decorate your lab coat. It depends. You can tie dye it, you can use fabric pens, you can embroidery. You can use LEDs. One class I had, they really got into this. They were having blinking LEDs on their lab coat, blinking LEDs on their posters. It was pretty interesting. Embroidery, iron patches, that all that's fine. And I like color. So let's see, what else do we have here? Yes, regarding the lab manual. I'm leaning towards just providing the thing for you digitally, and I'm going to mark it off as the new vendor that took over. I haven't put a due date on the safety contracts yet. The waiver and the safety contracts are due this week. I'm going to put it Friday. I haven't put it on yet, but
Are we also going to get the waiver and safety contract in lab class today?
yeah, I have it digitally and also have it in class in the lab.
Thank you. It's just I'm not enrolled into the class, so I'm not able to access any of the camera stuff yet.
Say the second part again.
I'm not enrolled into the class. I'm still currently on the wait list, so I'm not able to access the safety contract or waive
Oh,
contract
right.
yet.
Just wait till you get into Canvas, then do it. If it's past the due date, that's fine. In fact, I should push the due date back because of the stupid e-service is not working. So you can't add anyway. I'll put
I'll
it,
be in class today, so I can receive the paper copy one.
well, From the chancellor, they said it's working, but it's working extremely slowly, or not at all. So um, and the lab coat decorating is due anytime in the semester. Doesn't matter when. So you can start on it, and if you're embroidering, you can do a little embroidery. One student up in Sierra last semester, she wants to be a toxicologist, and she was really into poisonous plants. So she embroidered on the back of her lab coat the plant, and then she embroidered the structure of the chemical in it that made it poisonous. It was really cool. Um, Another person paid her sister to embroider on her lab coat. Um, and another person did sponge dyeing as opposed to tie dyeing. And so she started at the bottom of her lab coat, a real dark red, and then gradually kept diluting it and kept sponging it up to the top where it was no color at all. So you can do that kind of stuff. You can do combinations. It's whatever you want to do, as opposed to white. Okay, Brianna, regarding the project, if you go over to share, if you go to project under files, these are examples, mostly good, some are not so good, of past. I've done thousands of these because I've been doing for like 20 something years. And in my non 306 class, 305 and 300, I do them as extra credit. Actually, 305 requires a poster, or requires a project. It's a 300 class, and Sierra doesn't require it either. So I do it as extra credit up here. Anyway, these are examples of some posters. They're this is a drug that was synthesized in Russia. It's called crocodile, and it's similar to a lot of the uh, heroin-like drugs. And it's the problem is the high is higher than heroin, and it doesn't last as long, and it dissolves tissue on the injection site. These pictures didn't come through very well, but it actually dissolves the tissue. It's really awful stuff. Anyway, so 3-panel poster, and then you're going to have a 1,000-word essay that goes along with it. Now you can have anything as long as it's got organic chemistry and biochemistry in it, you can do it. Chemistry of dying, one person did. The what else? Manuka honey. How does Manuka honey, work in terms of antioxidants, etc. What else? Caffeine. The difference between coffee and tea in terms of any of that stuff, and go through here and just look these over and think of the poster as kind of the multimedia part of your essay. Try to get a black poster also, because everything pops with a black poster. Otherwise, it's white on white, and this is on mascara. There's nutritional stuff you can do. I'm not sure what that is. Anyway, and then the essay is going to be a 1,000-word essay. It's not very long, and you're going to have a poster that goes with it. Did that help? Was it Brianna that asked that question?
Yeah, thank you so much.
Yeah, okay. All right. Okay, I think I've hit on most of these. Let's see. Yeah, Brianna again. Don't worry about the safety contract. Did you go, are you a Monday lab or Wednesday?
I'm Wednesday lab, so I'll be there today.
Okay, I have copies of all this stuff, the hard copies. So just
Okay.
grab. There's three things you need. You're gonna try to pair up with someone for a lab partner today in lab. You're gonna do an inventory of your drawer. Um, and also grab the safety contract and the waiver today for lab. So it's not going to be a long lab today. Monday we had people hang around for hours, but you don't have to be there for hours today. Okay, any other questions? And you may work on your worksheet um, in lab or do it at home. You haven't had enough. Well, you've lecture-wise, we covered alkenes today. You can there's about 8 or 9 worksheets on the dry labs. The first 2 or 3 you should be able to start on. And we'll cover alcohols on Monday. And then we're going to start integrating the 3 subunits together. Okay, so I need to get going here because I don't want to be late. Because the traffic is iffy. Monday, the traffic actually stopped on I-5. I live in Natomas. And so I get on I-5 and go south and get off at Sutterville. And traffic around where I-80 intersects I-5, it always slows down. And Monday it stopped. It was driving me crazy. So,